Hello, I'm Hannah. I'm a PhD student at the University of Reading, looking at the dynamics of Arctic cyclones, including the interaction with sea ice. So Arctic cyclones are synoptic scale features. They're the major weather hazard in the summertime Arctic, producing strong winds and impacting the sea ice over large areas. And they're currently about 1 to 2 days less predictable than mid-latitude cyclones. So there's a need for a better understanding of these systems. And one of the biggest uncertainties in our understanding is the interaction with the surface and the sea ice. So today I'm going to be talking about the role of friction in two contrasting summertime Arctic cyclones. So yeah, my work so far has mostly been focused on the processes in models, but my project's also linked with a field campaign which happened in the last month in Svalbard, and I will talk about this later also. Okay, so starting with the motivation for this work. We know that boundary layer friction acts to reduce the intensity of mid-latitude cyclones, and the dominant frictional process is often assumed to be Ekman pumping, where friction forces convergence and a secondary circulation that acts to spin down a barotropic cyclone, or barotropic vortex. But in baroclinic cyclones, the complete role of friction is more complicated than this, and I will get onto this later. So friction in the context of Arctic cyclones hasn't yet been investigated, and differences compared to mid-latitudes are expected for several reasons. Firstly, due to the sea ice, especially with enhanced surface roughness in the marginal ice zone. Also due to longer-lived systems in the Arctic, so friction has a longer time to act. And then also due to different cyclone growth mechanisms and structures. And this is mostly what I'll be talking about today. Okay, so with this work, the main research questions are to firstly understand what the nature of the frictional processes acting in different types of Arctic cyclones are compared to mid-latitudes, and then to understand what the impact of the frictional processes is on the Arctic cyclones. So with this work, I'm going to be using a potential vorticity framework. So PV is a measure of both spin and stratification. And importantly, it's not conserved in the presence of friction. So friction in the boundary layer means that this tendency of PV will be non-zero. And I'll be using this depth-averaged PV tendency equation in the boundary layer, which was derived by Cooper et al. And the important things to know are that there are two terms. The tau S is the surface stress, and this opposes the surface wind, so this is like the momentum flux. And a constant density and a linear flux gradient have been assumed in the boundary layer to derive this. Okay, so this is our equation. As I said, it has two terms, each representing a distinct frictional process by which friction impacts synoptic scale processes. And I'll show you what they look like in typical mid-latitude cyclones. So firstly, Ekman friction. This is proportional to the curl of the wind stress, and therefore the vertical Ekman pumping. So in cyclones, this term will be negative, assuming the boundary layer is stably stratified. And then the second term is less well known. This is called baroclinic generation, and it arises due to horizontal vorticity due to vertical wind shear across the boundary layer. And the sign of this term depends on the orientation of the surface stress and the gradient of potential temperature above the boundary layer, which is equivalent to the low-level thermal wind. So in typical mid-latitude cyclones, positive PV is generated along the warm front, where the surface winds oppose the low-level thermal wind. And so how does this positive PV impact the cyclone? Well, this positive PV is transported above the boundary layer, where it acts as an insulator to reduce the coupling between the upper and lower levels. And so this will act to weaken a baroclinic cyclone. And this is actually the dominant frictional process in mid-latitude cyclones. Okay, so now actually on to Arctic cyclones. Here I'm using two case studies from summer 2020. They were the strongest cyclones that occurred in this season over the ice, and they both had quite different developments, and they each represent the two types of cyclone development that you see in the Arctic. So firstly, Cyclone A occurred in May 2020, And this was a low-level dominant cyclone. So it was initially dominated by vorticity at the low levels, which means that it had a low-level warm core thermal wind structure. And so it developed as part of a baroclinic wave, like a typical mid-latitude cyclone. And in the 850 hectopascal potential temperature, you can see the cyclone warm sector, and you can see that the cyclone develops in the middle of this upper-level trough ridge pattern on the tropopause. But now Cyclone B occurred in July 2020, and this was instead an upper-level dominant cyclone, so it had a cold core thermal wind structure. It developed with a tropopause polar vortex, or a TPV, and around the time of maximum intensity here, you can see that the cyclone is vertically stacked, with the low-level cyclone vertically stacked below this axisymmetric TPV. As you can see that the two structures look quite different at around maximum intensity. So now I'm going to calculate the frictional PV tendencies. And in my work, I've actually done this from IFS model runs, but here I'm just showing them from ERA5 reanalysis to keep things simple. So on the top row is the Ekman friction term, and these are both negative. So this is consistent with Ekman pumping, as you would expect for a cyclone. But the baroclinic generation term differs for the two cyclones. So for cyclone A, this is positive along the warm front and then wrapping around the cyclone center. And this looked like sort of the mid-latitude cyclone composite that I showed previously. However, cyclone B, this term is negative. It's looking quite different to cyclone A. So these are instantaneous PV tendencies at around the time of maximum intensity. We can also look at how they evolve with time by taking an average. This magenta circle shows the 750-kilometer radius about the cyclone center. We take the average of that following the cyclone through its lifetime. And these are the time series. So the red line shows the Ekman friction term, the blue line shows the baroclinic generation, and then the gray and black line show the time of maximum growth rate and maximum intensity for both cyclones. So generally, the Ekman friction term is negative, and so I'll focus on the more interesting baroclinic generation term. So during the baroclinic growth phase, the baroclinic generation term is positive and large, and then after maximum intensity, this term drops off and reduces in magnitude as the cyclone matures. But then for cyclone B, this term is also positive during the baroclinic growth phase, but it has a smaller magnitude, which indicates reduced baroclinicity. And then it begins to undergo this transition to this cold core columnar vortex structure. Oh, can I go back? There we go, yeah, sorry. And then this term becomes negative and large and stays negative for several days. It's clearly this baroclinic generation term that differs between the two cyclones, and this indicates different frictional mechanisms. And in the future, I'm going to be investigating this using idealized modeling. So one simple way to think about the impact of friction on cyclones is to use the dynamical concept of thermal wind balance. So thermal wind balance links the vertical wind shear with horizontal gradients in potential temperature. And this is relevant to this baroclinic generation term because this concerns vertical wind shear over the boundary layer. And so by considering, I don't want to go into all the details here, the slide has got a lot on it, but by considering how friction changes the vertical wind shear across the boundary layer, it can be shown that friction acts to decay the low-level warm core structure of low-level dominant cyclones, but amplify the cold core structure of these upper-level dominant cyclones. So this is a really simple way, just using thermal wind, to show you that friction has the opposite impact on cyclone structure. But I want to investigate this more rigorously in the future using idealized modeling. And if I've got time. In both cases here, friction is causing low-level cooling. And a general behavior of Arctic cyclones after they've matured is to obtain this cold core barotropic structure. And so it's possible that friction is contributing to this. Okay, so now on to the fill campaign. The Arctic Summertime Cyclones field campaign took place literally in the last month in Svalbard. And we're aiming to fly through Arctic cyclones and to sort of measure this Arctic cyclone sea ice interaction. So the aims were to fly at low levels, as low as 50 feet, to measure turbulent fluxes over the sea ice and also measure like the surface properties of the ice. But then also fly anywhere up to 10,000 feet to obtain boundary layer profiles and to map cyclone structure. And so to do this, we were using British Antarctic Survey's Twin Otter aircraft, kitted out with meteorological instruments. And so the field campaign was successful. There was a total of 17 flights in the month that we were there, with a mixture of flights at low level over the sea ice, but then also managing to fly through several cyclones. And I just want to bring up one relevant flight of an Arctic cyclone that was to the south of Svalbard. And so the flight plan was to fly through this bent-back warm front of an Arctic cyclone. And you can see the front in these really strong winds at 950 hectopascals from the Met forecast. And so we transited out from Longyearbyen to the front, and we were able to cross it at several different heights to map out the structure. But importantly, we'll be able to deduce the frictional baroclinic PV generation from this, from measurements of the wind in and above the boundary layer. Okay, so conclusions. Arctic cyclones can be low-level or upper-level dominant, and I showed an example of each case. And I showed that the frictional mechanisms acting in those two cyclones are different due to the different cyclone structure. And I also showed that friction then has the opposite impact on cyclone structure. So in a low-level dominant cyclone, the warm core structure will be decayed, but in the upper-level dominant cyclones, the cold core is amplified by friction. And I also suggested that friction may be related to this persistent cold core barotropic structure of mature Arctic cyclones, in contrast to mid-latitude cyclones, which tend to more quickly dissipate. And so for future work, I'll be characterizing these frictional mechanisms using idealized modeling and sensitivity experiments. And then also, finally, once we understand these processes, is to evaluate this frictional PV generation term from models with these new observations from the field campaign. So that's everything I have. Are there any questions?
Thank you, Anna. We have time for a couple of questions. I can ask one. Oh, this one's at the back there.
Thank you. Very nice talk. Given the complexity of cyclones, even in models, of course.
Say again, sorry?
Given the complexities of cyclones in models and the two types you show here, could you give us probably an idea of how your idealized experiments might look like? Like, what do you neglect in that cases, and how should that be done?
The main thing is that we'd have to assume that they're circularly symmetric. So the plan is to use really idealized models like quasi-geostrophic and semi-geostrophic. And then, we have these sort of axisymmetric setups, and then change the surface forcing. So here I spoke about friction, but we could also look at sensible heat fluxes as well.
I also think this is a really great talk. It's a fascinating thing. I'm particularly interested in the way cyclones evolve statistically and these kind of warm air injection events and the way transport happens. And these two case studies, have you looked statistically at how that case B, these longer-lived cold core cyclones evolve, and if these are responsible or more closely associated with those injection events?
Sorry, what do you mean by statistically?
On more than a case study basis, right? So like warm air advection, for example, like quantifying those
No, I
properties.
haven't. I've only looked at these case studies. But in general, these, I didn't say it, but these, like the cyclones like Cyclone B that develop with these TPVs do have a longer lifetime. Just very briefly looking at statistics of like cyclones over the past 40 years or so. But yeah, I'm not sure about these injections of warm air that you're talking about, I'm afraid.
Okay, I think we better move on. Thanks